So, welcome to the next lecture of the series. In the last lecture, we have designed the parameter design of DC-DC converters. We have derived the relation of the peak-to-peak inductor current and the peak-to-peak output voltage delta V naught and delta L relation with respect to the converter parameters and also the peak inductor current. So this is summarized in this table which you can see here. So, and based on this we have decided the range of the suggestible or the permissible range of operation of each of the DC-DC converters. So you have to optimize the peak so assumption is whenever we are seeing we want to optimize it, we should have some assumptions. Assumptions are V in, I load, or you can say R, FSW, L, C are constant, and each of them are known to us. So from the expression which we can see in the table, it is concluded that for a buck converter the duty ratio should be high to reduce delta IL and V naught, because if we plot it will become like this. We got two regions of operations for a buck converter, that is at the low range of duty ratio, and the second one is at the high duty ratio range. And out of this we have to select we have to see which range is more suitable to operate. Apart from minimizing delta L and delta V naught, we have to minimize IL max. IL max defines the peak amount of current which can pass through the inductor. So while designing of an inductor, we should take into consideration many things. One of that things is the peak current. Then we also take into consideration the type of the core which we need, ferrite core, sandust core, then the shape of the core, toroidal core, EE core, then the window product. Then while mounting the coil on it or any copper wire on it, we have to see the gauge of the wire based on the current rating and the current density of the wire. And as the current density increases, the wire becomes thick, which will limit the window area. So which will limit the number of turns which we wound on the inductor, as inductance is proportional to N square. L equals to N square by reluctance. So the reluctance of the coil you can set by using the ferrite core material. The choice of the ferrite core material also decides the peak flux density B, which you can decide. And if you want to, for the same given number of turns, if you want to increase the inductance or you want to decrease the reluctance, so you can introduce air gap in it. So these are the multiple factors in which you have to design inductor. So one of the important factor is the peak inductor current. So we assume that the load at which all three converters which operate is constant, and so that's why I load or R both are constant. Vin is also constant. We are not changing the input voltage. The source voltage is constant. Switching frequency and L and C are fixed, they don't vary. Then what we saw that for buck converter we got two ranges of operation. For the second range, this particular thing D into V in by R, this thing we have to reduce. So that's why we have preferred the R2 region, because we saw that for the capacitance we have to also minimize delta L by delta V naught, because capacitance is a function of that terms, which we have also mentioned here. So this is for tuning the L and C. So we saw how in what regions the converter will operate. Now we'll just quickly see no load operation of the converter, and after that we'll start with discontinuous mode of operation. No load operating mode of DC-DC converters. So what happens when there is no load on the DC-DC converter? First we'll see for a buck converter. So and this is open circuited. I load is 0, so this is IC, this is IL, this is diode D1, this is switch 1. To this switch, PWM pulses are given. In PWM pulses, we compare the duty ratio D or D, we compare with this. What we do is, if it is greater than 0, then S1 will give. S1 is between 0 to 1, like that, of this form. Practically, this is means theoretically it is correct for you can directly give 0 1 0 1 this signal to the switch, but practically if you want to develop a hardware of any converter, the voltage levels, that is the logic level with respect to 1, that is 3.3 or 5 volts, is insufficient or not sufficient to turn on the power device, same power MOSFET. So we need a gate driver circuit which will boost up this 0101 or 0 to 3.3 voltage levels to 0 to 15 volts, 18 volts, like that. So it's a gate driver circuit. So this D is different. This is the duty ratio, and this D1 is the diode, to avoid the confusion. So what happens when there is no load on the converter? What we saw here was that the capacitor. So here, as load current is 0, IL equals to IC, which means that this is IC having some average value. So what happens here in this case is, this should be typically IL value, IL, but the average value of IL was, say this is IL. So for no load, IL equals to IC. So let's assume that we are drawing IL and IC. So average value of IL was the load current, but this is 0, which means that this waveform should go down. So if we draw, then it will be of this fashion. This will be the this should be the inductor current, IL. Now you see that the inductor current becomes negative. Negative IL, which means that the inductor current will change its polarity. Now say that, okay, so this was for on time, D into T switching, and this period is off period, 1 minus D into T switching. Or you can also write this, you can shift, you can write this as off time and the other one as the on time. So it is 1 minus D into T switching. So what happens is that, okay, let us not write like this, let us write in this way only. So what you find here is that in 1 minus D switching time, the inductor current is negative as well as positive. So positive inductor current is not a big deal in it when the switch is on. So what happens is, when the switch is on, diode is off, the inductor current becomes negative for some time, so what happens is, this current has to flow in the reverse direction. So the switch should be a 2-quadrant switch. So S1 should be 2-quadrant switch with respect to the current flow, which means that if we see I versus V, it should pass current of both the polarity and it should block voltage of one polarity. So this is 2-quadrant switch, which means it can be MOSFET or IGBT with anti-parallel diode. parallel diode. So S1 can be this is gate, drain, source, or so diode has the MOSFET has inherent freewheeling diode. So this we have to either see the packages of the IGBT which has inherent inbuilt anti-parallel diode, or we should add a separate one to it. So it can be MOSFET or IGBT. So that's why S1 is this type. So it is not a problem when the switch is on and the inductor current is negative. It is problematic when the switch is off or when the diode is conducting, but the inductor current reverses its polarity. That is a problem. So in this case, what happens is, let's say the switch is off. Now our concern is in the 1 minus d into t switching time. Here, for this time, inductor current is negative. So what happens here is that the diode can conduct current only in one direction. It cannot allow reverse direction current flow. If it allows that, it means that the diode is reverse bias. In that case, D is also off and S1 is also off. So this current will be not valid. Similarly, this negative current also will be not valid. Why? Because you can easily shift the coordinates and you can just make from here to here as on time, D to TS, and here to here as off time, T off, which means that this becomes like this. This becomes IL. This portion gets clipped away. So this results in discontinuity or discontinuous mode of operation. Which is also called as DCM. So this is continuous mode of operation. Not this one. The one which we saw till now is the continuous mode of operation. This is the discontinuous mode of operation. So any DC-DC converter, if the load is 0, it results in discontinuous mode of operation. Why? Because of the diode. If we add a switch, same two coordinate switch just like S1 in place of diode, then it can be continuous mode of operation. But if it is a diode with the no load, then it becomes discontinuous. So this waveform of IL becomes equals to IC. So now a very big problem arises, which is the average value. This has some average value of IL, which means that IC average is some average value which is not equals to 0, which means that amp second balance is violated. So now what happens if the amp second balance is violated? IC is C dVc by dt, which means that Vc is integral IC of t dt plus Vc of initial condition. So this was the area under IC versus time graph, which means that the area above the what you say, t equals to 0 axis equals to area below the t equals to 0 axis. Means in each switching cycle, the capacitor is to charge and discharge. Now this results in the capacitor continuously charging. Now what happens if the capacitor and no discharge time and no discharge? Why no discharge? Since capacitor discharges through load only. Why can't it discharge through any other circuitry of the present buck converter? Is because of the diode. So it can discharge with negative IL if D1 was a 2-quadrant in current switch. But now D1 is a diode. So what happens is, what will happen is VC will keep on increasing. VC, or the average value of VC or average value of V0, will keep on increasing with time, which means that this is V0. So this is the average value. It keeps on increasing, though it becomes a serious problem. Then the capacitor voltage keeps on increasing because there is no voltage, because the amp second balance is disturbed. We'll see if the volt second balance holds or not. Volt second balance means the voltage across capacitor in one switching state, that is, if switch is on, it is of some polarity, means if the switch is on, VL is what? VL is V in minus V0. If the switch is off, VL is what? Minus V0. So in that case, what happens is the volt second balance may satisfy, but the amp second balance is violated, which results in the continuous increase of the output voltage. This may be a problem. The capacitor may blast because the charges kept on accumulating on the capacitor. So the capacitor may blast and will result in the malfunction of the power converter. This will result in the malfunction. But there is a plus point. There is a silver lining to this cloud. The capacitor does not blast, which is valid only for a buck or buck derived DC-DC converters. Why does it blast? Is because V0 is D into V in. So V in is constant and D lies between 0 to 1, or say from 0.7 is to D is to 1, less than 1, or say 0.99. This is the preferred range of operation of the buck converter. So what happens is, if D equals to D max equals to 0.99 or tends to 1, so therefore V0 max is 1 into V in, which is equals to V in. So V0 never rises above V in, and thus the capacitor is safe. The capacitor can charge maximum to V in voltage, input voltage. If V1 equals if V out equals to V in, it means that no power is transferred between input and output. So buck converter has some inherent protection, which is due to the non-operating mode. So non-operating mode leads to accumulation of charge on capacitor, which may lead to blasting of the capacitor. Especially for buck converter, it does not happen because Dmax is what? 1. So V0 max can be 1. So, but for boost, buck boost and their respective derived converters, what is V0 max? V0 max is V in by 1 minus D max, and this is for boost, and V0 max is D max by 1 minus D, we'll write mod D max into V in. So D max equals to 1. So V0 max equals to infinite in boost as well as buck boost, because anyways buck boost converter acts as a boost converter when D is greater than 0.5. So D max is always in the boost mode. So boost converter or buck boost converter should never be operated on no load. So boost and buck boost converters should never be operated on no load or NL conditions. This is the reason. As the amp second balance is invalid, the voltage keeps on building. Buck converter has a protection because Dmax is 1, so V0 will never cross V in. So the capacitor is safe. But for boost and buck boost, ideal, so we derived V0 as V in by 1 minus D for boost and D into V by D by 1 minus D into V in for a buck boost converter. That we assumed non-idealities. But even if we neglect non-idealities and if we put Dmax in this equation, the V0 max will be infinite, which means that the voltage will keep on rising. So the capacitor may blast. So we should never operate boost converter on no load. Or you can, so whatever is the limit of Dmax, you have to reduce the limit of Dmax. So Dmax, instead of being 1, you have to reduce it. So you can use the preferable mode of operation of your converters. So either you put some load on the on these boost and buck boost converters, or you reduce Dmax. You reduce the Dmax, or what you do is, for your Dmax for a particular application, select what should be the V0 max, and the rating of the electrolytic capacitor at the output should have at least greater than that V0 max voltage, so that capacitor is safe. So that's why the analysis of no load is necessary for designing DC-DC converters. Here we saw that we can find this. So we can find the minimum load. So these converters operate on some minimum load. Operate on some minimum load. So some minimum load is applied to this converter, R minimum or I load minimum. We can find it. We can easily find what should be the minimum load across a boost and a buck boost converter by using this voltage relation. By using this voltage relation, you can derive it. So you can derive the minimum load across a boost or buck boost converter because the inductor current waveform is same for all the three converters. So what you can do is say that the inductor current waveform just touched the t equals to 0 axis. This is IL, this is IL max, and this is what? Capital IL. This is IL minimum, and this whole is delta IL, peak to peak. So to find R minimum, what you put is IL minimum, you put as 0. So what you do is you put IL equals to 0. What is IL minimum? It is capital IL minus delta IL by 2. From the average value, you subtract the half of the ripple value, half of the peak to peak ripple value, or half of the average to average to lower peak value. So this you can easily derive. So for a boost converter, what is IL? For a boost converter, the inductor is placed at the input side. So IL will be I load by 1 minus T, right? So therefore, but I load is I load minimum, that is V0 by R into 1 minus T. Because we have to find R minimum. Let's assume that V0 is V0 steady state and D is D max. So I'll write 1 minus D max, that is IL, average value of IL during that instance when IL minimum just touches 0. So therefore if you put here, what you will get? Capital IL is delta IL by 2. So delta IL we can substitute from the table which we have derived. Delta IL was V in D into 1 minus T, V in into D into 1 minus T. Sorry, that was boost converter. V in D by L F switching. So it is V in into D by for a boost converter, V in into D by L into F switching. L into F switching. This divided by 2. This is now capital IL equals to capital IL. So therefore V in into D, let's at the last substitute D as D max, R as R minimum, that later we can substitute. As of now we'll just put 2L into F switching becomes equals to V0 by R into 1 minus T. So again you can write V0 as V in by R into 1 minus T whole square. So this V in gets cancelled with this V in. So if you take R in this side, so dy to L F switching equals to 1 by R into 1 minus T whole square. If we find R will be what? 2L F switching divided by D into 1 minus D whole square. This is the R minimum. So therefore this is the R minimum equals to, let's say the inductance is fixed, it is not changing, switching frequency is fixed, divided by D max into 1 minus D max whole square for a boost converter. This is the minimum load which you have to apply on a boost converter. Similarly, you can derive for buck boost converter. You can derive this for the buck boost converter. So for a buck boost, how to derive? Simple. Capital IL is delta IL by 2. Now you write capital IL in terms of this. So without seeing the converter, I just have to remember that the inductor in the boost converter is placed here. It is like this, because for load you have to draw only KCL, so you have to consider only nodal analysis, and here there is a switch. So this is IS1, this is ID1. So somewhere here there is a capacitor, and this goes to, sorry, reverse polarity is there because it's a buck boost converter. So like this. So this is I load, capital I load, and ID1 equals to I load, and this is IL. When the switch is on, IS1 is IL. When the switch is off, ID1 is IL. So ID1 or I load equals to 1 minus T of IL. Or you can write V0, I load, that is V0 by, now we are taking mod of everything, don't put the sign. So I load is V0 by R equals to 1 minus T into IL, which can further be written as D by 1 minus T into V in by R. This is the correct expression. Therefore capital IL becomes D into V in by 1 minus D whole square into R. This we have to substitute here. So therefore, and delta IL we write from the table. I think we have derived delta IL from the table. What is delta IL? It is same, V in D by L F switching. So therefore V in D by 2 L into F switching. Why? Because it is delta L by 2. Yes, V in D by L into F switching by 2 equals to capital IL, that is D V in by 1 minus D whole square R. Simple. Cancel out V in and find and D also will be cancelled. So therefore what is our 2LF switching divided by 1 minus T whole square. This is the R. So therefore R minimum. So why I have written here this equation is, I will use it and I will tell you why am I using it. This is equation 1, this is equation 2. Equation 3 is R minimum for boost converter, and equation 4, which I will be writing now, this is 2LF switching by 1 minus T max ka whole square. This is for a buck boost converter. This is equation number 4. Okay, so now we have derived what should be the minimum load across boost and buck boost converter. Now we'll see the discontinuity. We have already started with discontinuity in DC-DC converters. We saw that because of the diode, this thing happens. So no load operation is one of the reasons of discontinuity. So in the discontinuous mode of operation, we will see the reasons. Reasons for discontinuity for a random DC-DC converter. First is the no load operation. Second is L less than L critical or L less than L minimum. This is one of the reason of discontinuity. And the third very obvious reason is the due to diode D1. So reason number 1 and 3 are interrelated to each other. If I tell you what is the circuit element inside any DC-DC converter which leads to discontinuity, then you should quickly say that it is the diode. Because if diode is replaced with a switch, then nothing will happen. It won't be discontinuous. So this is the ultimate reason. You can write further reasons as if we see the expression of in the previous lecture, means in these notes, it was a function of see, R minimum for boost as well as buck boost converter was a function of L into F switching and T max. So you have to write switching frequency and D max also should be the reasons. Switching frequency, switching frequency 4, 5 and T max is one of the reasons. D max equals to 1 is one of the reason. If you reduce D max, then the range of operation for the continuity will increase. So these are the reasons affecting or leading to discontinuity. But this cannot fix discontinuity. Why? Is because again inductance is a function of switching frequency. Inductance is a function of input voltage. Inductance is a function of duty ratio also. So these are the point number 4 and 5 are the reasons where you can handle or vary the range of discontinuity. If you shift, instead of making Dmax as 1, if you make Dmax as 0.7, then the range of continuity will be more, given that the converter still operates at no load condition. The range for which you can get a continuous mode of operation is increased, but you cannot get rid of discontinuity. If you replace that with a switch, then discontinuity is gone. Whatever may be the load, whatever may be the inductance, whatever may be the duty ratio and switching frequency, it is gone. So ultimate reason is D1 and ultimate solution is also D1. These are the reasons for discontinuity. The choice of inductance plays a major role in the designing the discontinuity. So let's find out critical or minimum inductance. Which is L minimum for any converter. First, for a buck converter. So what should be the minimum inductance above which, if we select an inductance below this value, it will be discontinuous, and if L is greater than this value, then the R converter will operate in the continuous mode of region of operation. So again, the basic principle is put IL minimum equals to 0. This we have already done in the previous lecture, so we can directly copy paste it. So in this expression whatever we derived for a boost converter and a buck boost converter, we didn't find what is the minimum load requirement for a buck converter, because even if we find, we'll get an expression, but even if the minimum load we don't add on the buck converter, the converter is safe because Dmax is 1. So V out can never be more than V in, so it is a safe, it will operate in a safe condition. That's why we have to derive only for buck converter. For boost and buck boost converter, we'll use equation number 1 and 2. Equation 1 we derived using, if we substituted IL minimum as 0 without substitution of D as D max, R as R minimum, nothing. That's why I have mentioned here separately R equals to this and R min equals to this. Similarly for buck boost, so that we can use it in this section. So I hope now you got it, that from equation number 1 you can get L in terms of D, F switching and R. Similarly, if you use equation number 2, you will get L minimum for buck boost converter, that is R into 1 minus D square by L into F switching. So we can directly copy paste from here and write for buck converter. Okay, we have to derive. So what? IL minimum, that is capital IL is what? Delta IL by 2. Capital IL is what? I load, which is V0 by R. V0 is d Vin, so d Vin by R. We have to write in the simplify into the most simplified form. We don't have to keep it in the form of I load or V0. V0 can be further replaced as d into Vin. So assuming that the conductor has just touched the discontinuity line, so by avoiding the uncertainties, this is the expression. And what is delta L? Delta L we have to copy. Delta IL expression for a buck converter, this one. So let's copy. Let's erase these lines. Okay, it can't be copied, so we'll write it. So it will be V in into D into 1 minus D by 2LF switching. These lines are not going. Okay, fine. We'll delete it. So this is the expression. You can easily find L from this expression. V and D gets cancelled. So it will be 1 minus D by 2LF switching equals to 1 by R. So L becomes L critical is equals to, in the numerator we have R into 1 minus D. So R into 1 minus D by 2F switching for a buck converter. L critical is this. So for a boost, using equation number 1, we can I'm directly writing because we have already derived. L critical was D into 1 minus D whole square into R divided by 2F switching. And for buck boost, we use equation number 2. So L critical was 1 minus D whole square R by 2F switching. These are the critical inductances. So L has to be greater than L critical for continuous conduction mode, else you will get discontinuous conduction mode. This is continuous. Continuous conduction mode, and this is discontinuous. So L has to be greater than this value. So whenever you are so what you do is, we have already derived the inductances, I think in the previous lecture. These ones here, yeah, these are the L values for each converter we have derived. This is for the buck converter. Yes, this is for the buck converter. L is V into D into 1 minus D by delta L into F switching. Similarly for boost, it is V into D by delta L into F switching, and for buck boost it is V into D by delta L into F switching, which is same. So now you got two expression for inductor for selecting the inductors. In the previous lecture where we have derived the inductances as a function of delta IL, that was like when you know what should be the ripple of inductor current, allowable ripple, and based on that you found the inductor. This is when you found the inductor by considering that I minimum is 0. That is when the inductance or when the mode of operation changes to discontinuous. So what you have to do is L, you have to find maximum of L critical and L as a function of delta IL for any converter. This you have to keep in mind while designing the inductor, because the inductance expression which we derived in the last lecture was a function of delta IL. So you have to select the maximum of it, and you have to use this greater than equals to maximum of this comma this, because if, let's say, if critical inductance is less than this LF of IL, so even if you take maximum, it will be L will be greater than L critical, which will be continuous, and so the conduction mode will be continuous. And if you select that L corresponding to this F of delta L, then you will get delta L as expected. So for inductance, you have to take maximum of L critical and L as a function of delta L. But for capacitors, you can directly select the capacitors based on what we calculated in the previous lecture, which was a function of delta IL as well as delta V0. Okay, so this no load thing we handled in the last lecture. By finding R minimum. If you put this R minimum, your converter for a buck boost and buck boost converter will never be in discontinuous mode. So either you find L critical or you find R minimum. It is one and the same. Because this expression number, I think 1, 2, 3, 4 was there. So 5, 6 and 7. Either you find L critical or you find R minimum. If you put R minimum across the converter as a minimum load, then it will be continuous. Or if you select L greater than L critical, no need to think about R minimum. It will always be continuous conduction mode. So we saw this. D1 I told you. The remedy is replace with a 2-quadrant switch. Then there is no need to do all the analysis. Then it is F switching. As you know that L critical is a function of F switching, or R minimum is a function of F switching. So if you increase the switching, what happens for all of the 3 converters, it is inversely proportional. Let's say that R is constant and only we are seeing F switching. So as we increase F switching, the L critical will decrease. Let's say initially we have got some L critical and we have selected L somewhat greater than L critical. Now suddenly my operating switching frequency increases. Now what happens is, for the same inductance which I have designed earlier, as L critical reduces, which means that new L critical may be less than my previously selected inductance. So what happens here is, if the switching frequency increases, the size of inductance requirement and then the bulkiness can come down, but it can also result in discontinuity. So FSW has to be low. Switching frequency has to be low. If switching frequency is increased, it results to discontinuity. Same fifth point we also tackled. That is, instead of making Dmax as 1, reduce it. Reduce Dmax. Make it less than 1 based on the permissible or preferable range of operation for each of the converters. So this was the discontinuous mode of operation. In the next lecture, we will see the waveforms of each of the buck boost and buck boost converter operating in DCM or discontinuous mode. Then as the converter operates in DCM, then the voltage gain, that is V0 is dVin for a buck, V0 is Vin is V0 by 1 minus D for boost, and V0 is D by 1 minus D into Vin for buck boost. It is not valid, because those expressions are valid only when it is a continuous conduction mode. As the waveform of inductor current itself changes, all other waveform will change. That's why the volt second balance will have, earlier we had only 2 times, T on and T off. Now here we'll be having 3 times, T on, T off, and the one case where diode as well as the switch was 0. So just to explain you how this we saw here, right? We saw here no load operating mode here like this. Yeah, here what we saw here, that positive inductor current when the switch is on is not a problem. Negative current when the switch is on is also not a problem, because the say that the device has freewheeling diode. So then the negative IL will flow from the diode like this to the source. Then when the switch is off, the inductor current is positive, then that is not a problem. But when the inductor current is negative and the switch is off, then IL becomes negative. In that case, the diode is reverse bias, which means that now the diode is off, switch is off. So one more state comes into consideration for discontinuous mode. Earlier it was only two possible states. When switch is on, diode used to be off always. When switch is off, diode used to be on always. Now a third condition will come where the switch is also off and diode is also off. The diode is off only because of the negative or the reverse polarity of the inductor current. So a third state will come into consideration. So our volt second balance will be V on into T on plus V off into T off plus one more V, that is the time or that is the value of the inductor voltage when switch as well as diode is off into T off, into some T. That T is when, that T is this time during which the switch is off and the current is negative. That is that T. So third condition, a third switching condition comes into picture for discontinuous mode. Then the similarly for amp second balance, the relation between input and output average currents will also change. Then all the analysis will change. We'll see what are the advantages of discontinuous mode over continuous mode. We can, because the gain V0 by Vin will also change. For the same converter, does CCS give more gain, voltage gain, or does DCM gives more voltage gain? That also we will see in the next lecture. Thank you.